Welcome again. In today's session we are going to discuss on the fracture of metals. So what is fracture? Fracture is nothing but it is a form of failure where the material separates into pieces due to stress at temperature below the melting point. So the fracture is termed ductile or brittle depending on whether the elongation is large or small. The steps in fracture, that is response to stress, there are two steps. One is a crack formation, another one is a crack propagation. So if you see fracture, there are two major types of fracture. One is a ductile fracture, another one is a brittle fracture. So the stages of ductile fracture are, first it starts with the initial necking and a small cavity formation, that is a micro voids are formed together, and the growth of micro voids, that is a coalescence of these voids to form a crack. Then the propagation of the crack around the neck, that is a shear strain at a 45 degree, then final shear fracture, that is occurs in the form of a cup and cone fracture. So okay, the interior surface of the ductile fractured metal is fibrous, irregular with signify plastic deformation. Coming to the brittle fracture, there is no appreciable deformation and crack propagation is very fast in case of brittle fracture. In most brittle materials, crack propagation by bond breaking is along specified crystallographic plane, that is cleavage planes. This type of fracture is transgranular, that is the crack propagates through the grains producing a grainy texture or faceted texture with the cleavage direction changes from grain to grain. Okay, so through grains is very dangerous. Okay, generally the metal fracture takes place along the grain boundaries. Okay, so if the crack propagates through the grains, it is very dangerous. Okay, that's what brittle fracture is, very dangerous. So you know, fatigue is also one type of brittle fracture. Okay, so in some materials fracture is intergranular. Okay, it passes through the grain boundaries. Okay, you can see these are the microstructure of a ductile fracture, brittle fracture and the creep fracture materials. You can see the ductile fracture, you can see lot of cup and cone type of fibrous structure. Okay, we can see that one, whereas in the brittle fracture you can see that a lot of rock like structure like striations, what you can see that in the same in the fatigue fracture surface. Okay, you can see some beach marks or striations, whereas the creep fracture, you can see the creep fracture it occurs at high stress and at high temperature. That's why we can see some of the white patches in the creep fractured metallographic structures. Okay, right. So coming to the ductile fracture, you can see these are the diagrams, shows represents the figure A represents the material starts to neck. Okay, when the material is loaded tensilely, a tensile load is applied on a material. Okay, so up to a certain limit, okay, it obeys Hooke's law, that is the stress is directly proportional to strain. Okay, where the elasticity come into picture, when the load is removed it will regain into original position. Okay, so beyond the elastic limit, okay, material starts to yield, that is when it reaches the yield point, the material starts to yield. Okay, so where the material tends to oppose the external forces, so that what happens, the material work harden. Okay, after work hardening, okay, so the material tries to pull out the external forces. Okay, so that only if you see the stress strain diagram, okay, so in the elastic region it will rise. Okay, and when it reaches the yield point, it starts to plunge down. Okay, for applied stress, the stress is not directly proportional. Okay, the strain will be less for the applied stress. Okay, then after some time, okay, when the load is continuously applied, okay, the material loses its strength and it will allow the tensile load to go predominantly over the internal energy, so that the material starts to yield permanently. Okay, so it continues until it reaches a point called as ultimate tensile point. Okay, where see this will the B in the figure shows the B where the small voids will form. Okay, so until after material reaches a ultimate tensile stress, the material will no longer can able to withstand the stress, so that what happens, a small necking will be formed. Okay, so on further application of the load, these necks, okay, these small voids will join together, that is coalescence together to form a crack. Okay, you can see the crack grows 90 degree to the applied stress, then it changes its direction to the angle of 45 degree, that is maximum shear stress direction. Okay, such that it separates into two after reaches a fracture point, okay, you can see a part of the metal will be taking the material from the another part, so that you can see a cup and cone type of fracture. Okay, so these are the 5 stages of a ductile fracture. Okay, necking followed by a cavity formation, then coalescence of this cavity to form a crack, then crack propagation, and finally the material will fracture. Okay, so in the left hand side you can see the materials, okay, how they break. Okay, so very ductile material, you can see a highly ductile material. Okay, it will separate until it continuously it's subjected to it is highly ductile, so that to after reaching the ultimate point, okay, it will starts to elongate until it separates into two, so that you can see a point like structure. Instead of a cup and cone, you can see a point like a point where it gets separated. Okay, next one is a moderately ductile material. You can see a fiber structure like a cup and cone fracture, whereas the brittle material, you can see brittle material, it breaks into two. Okay, after reaching the elastic limit, a small amount of plastic deformation will be taking place, which is negligible. Okay, then it will break into two. It is mostly perpendicular to the axial direction. Okay, axial direction of the force, right? So conditions of fractures are the tension, torsion, fatigue, creep, and low temperature brittle fracture, temperature embrittlement, and hydrogel embrittlement are the various conditions of fracture. Okay, so theoretical fracture crack strength and cracks. Let us consider a perfect crystalline material loaded in tension. The failure by fracture can occur if the bonds are broken and fresh surface are created. Right? If two atomic planes are to be separated, the force initially increases to a maximum and then decreases. So the maximum stress corresponding to F max is called as the theoretical strength, that is sigma T. Okay, the stress is given by sigma TFS, that is maximum tensile fracture strength. Okay, TFS, tensile fracture strength, is equal to sigma T, that is root of E gamma or nu divided by A naught. For many metals, nu is equal to 0.01 E A naught. Okay, so where E is the Young's modulus of the crystal, nu is the surface energy, A naught is the equilibrium distance between atomic center. This implies that theoretical fracture strength is in the range of E by 10 to E by 6. Okay, the strength of the real metals is in the order of E by 100 to E by 1000, that is much lower in the magnitude. So tiny cracks are responsible for this kind of behavior. Okay, so the applied force, you can see the applied force and the relationship between the maximum force, applied force, and the cohesive force. Okay, for aluminum, E value is generally 70.5 gigapascal and A naught is 2.86 Armstrong, and nu is 0.704 in 111 direction, and sigma T is 13.16 gigapascal. So cracks play the same role in the fracture of weakening as dislocation play for plastic deformation. Okay, so the much lower fracture strength is explained by the effect of stress concentration. Okay, well, you know stress concentration, if any notch or stress risers are present in the surface of the material, then that point is subjected to high stress concentration. Okay, so the applied stress is amplified at the tip of these micro cracks or voids or notches or surface scratches, corners, etc. These are called as stress risers. So each atoms attracts all neighboring atoms. In the center of the grid there is a hole, no material, therefore no atoms. No material, therefore no atoms. Now if a uniform force pulls this grid, then atoms will resist the force by holding each other firmly. So but when there is a hole, atoms are not present to resist the force pulling them apart. Therefore atoms of the adjacent rows near the hole will have to pull each other or other more firmly in order to compensate the atom shortage in the hole. I think you understand this one. Okay, when there is a hole, there will be no atom, okay, to produce the internal energy. Okay, so the atoms which are surrounding the hole, okay, have to spend additional internal energy to compensate the non-presence of the atoms. Okay, due to this, okay, stress concentration will be more at that point. Okay, so this is called as stress concentration. It is the concentration of resisting forces around a deformity in an atom to prevent pulling apart of the whole structure. Okay, so fracture is related to a propagation of crack leading to failure of the material. If there are no pre-existing cracks, then a crack needs to be nucleated before propagation to failure. So this implies that a material without any what stress rhesus or crack will not fail. Okay, so crack, so there should be some nucleation of the crack for the crack to propagate. Okay, then only the crack will happen in the material will break. Okay, so a crack is typically a sharp void in the material which acts like a stress concentrator or an amplifier. So crack in general have several geometries. Even a circular hole can be considered as a very blunt crack. A crack may lie fully enclosed by the material or may have crack faces connected to the outer surface. Okay, so fracture surface energy, okay, is greater than intrinsic surface energy to cause the material to for the crack to grow. Okay, you can see what is intrinsic surface energy. Always intrinsic surface energy, okay, is an internal energy which resists the external forces. Okay, so the fracture, if a material has to crack, if material has to break, then the fracture surface energy should be greater than the interior surface energy, then only the crack will start to propagate. Okay, so fracture mechanics is a beautiful subject, okay, in which there is a material resistance to fracture is characterized. In other words, the tolerance of the material to crack propagation is analyzed. So crack propagation can be steady, that is slowly increasing crack length with the time or load, or it can be catastrophic, unsteady crack propagation leading to sudden failure of the material. So when dislocation is to slips, crack is to failure. So I think you understand this concept. Under tensile loading, if the stress exceeds the yield strength of the material begins to deform plastically. So the area under the stress strain curve is designated as the toughness in case of uniaxial tension. Toughness relates to the energy absorbed to fracture. It is the property related to elastic region. Okay, so similarly, in the presence of cracks, we arrive a material parameter which characterizes the toughness of the material in the presence of crack, which is called as a fracture toughness. In most material, even if the material is macroscopically brittle, it shows very little plastic deformation in a uniaxial tensile test. Generally, this amount of stress, that is a plastic deformation, is very minimum. Okay, that's why we won't consider this as a into account. Okay, negligible amount of plastic strain. The brittle materials, okay, when it reaches when it crosses the elastic limit, it starts to break. Okay, so similarly, in the presence of crack, we arrive a material parameter which characterizes the toughness of the material in the presence of crack, that is a fracture toughness. So in most material, even if the material is macroscopically brittle, shows very little plastic deformation in the uniaxial tensile test. That is, there might be some ductility at the microscopic level. Okay, so this implies that in most material the crack tip is not infinitely sharp but is blunted a little. This further avoids the stress singularity at the crack tip, as well as we shall see that one in later. So you can see this is a sharp crack. Okay, so crack after sharp crack after crack tip blunting process. Okay, tip blunting process, we have seen that in fatigue Wood's concept, where the crack goes on sharpening, then blunt, then sharpen, then elongate, like that. Okay, the subject of fracture mechanics has its origin in the failure of World War II Liberty ships. In one of the cases, the ship virtually broke into two with a loud sound when it was in the harbor, that is not in the fighting mode. So this was caused by lack of fracture toughness at the weld joint, resulting in the propagation of brittle cracks. So breaking of Liberty ship has given the scientist about the study of fracture mechanics. Okay, so welding, why the Liberty ship breaks? Because of welding instead of riveting. Okay, which leads to which is the continuity of the structure. Okay, so welding, if you are if welding is carried out, then there will be since the structure is continuity. Okay, so instead of riveting, so residual stresses because of the weld structure, so continuity of the structure, the high residual stresses are entrapped in between the welded area, and micro cracks are originated. Okay, so these are the reasons why the Liberty ships breaks. And another reason is the cold water. Okay, cold water, iced water. Okay, and third one is high sulfur content, presence of high sulfur content in steel. These are the three major reasons why the material, that is material which is made up of made in the Liberty ships breaks. Okay, so coming to the characterization of the cracks, okay, the if you are characterizing the crack in the surface, okay, you can see in two methods you can characterize the cracks. One is in the surface, another one is the interior. Okay, so surface or interior, and the crack length. If it is in the surface, then the crack length is A. If it is at the center, the crack length is 2A. Okay, so crack orientation with respect to geometry and loading, and crack tip radius is also taken into account. Okay, now coming to the crack growth and failure, the crack growth criteria can be studied by means of Griffith, okay, which is an energy based phenomenon, and it is studied by Inglis, which is considered as stress based. Okay, so Griffith considered a global thermodynamic into consideration, whereas the English said that the stress is local. Okay, the crack is due to local stress and it is kinetic in nature, whereas the Griffith proposed that the crack is global and it is thermodynamic in nature. Okay, so for growth of a crack, it should be energetically favorable. Sufficient stress concentration should exist at the crack tip to break the bonds, and whereas a brittle fracture, cracks are sharp and no crack tip blunting, so no energy spent in plastic deformation at the crack tip. Okay, now coming to the Griffith theory. So Griffith realized the significance of micro cracks in reducing the fracture strength. He applied the mathematical work of Inglis in 1913 for an elliptical hole and developed a theoretical criterion of rupture based on the concept of minimum potential energy of classic mechanics and thermodynamics, which seeks a minimum total free energy of a system. So in Griffith theory, the theoretical strength is the microstructural fracture stress, which is actually reached in a very small volume of the material, while the mean stress may remain very low. Okay, so we can see the Griffith theory. So this is the derivation of the Griffith equation. Consider a crack length 2c penetrating through the thickness of the body under a macroscopic stress. Sigma c is much smaller than the dimension of the body, and the thickness is such that the plane strain condition can be assumed to apply throughout. These are the conditions which Griffith has assumed. Okay, since the body is under stress, the crack will open and you take the geometry of an ellipse. Okay, so we need to find an expression for the crack opening. The equation of the ellipse with major and minor axis is given by y is equal to b by a root of a square minus x square. So it is to be expected that the crack opening will be proportional to sigma and inversely proportional to E, that is the plane strain. Young's modulus is given by E dash is equal to E divided by 1 minus nu square. Okay, taking these factors into account, dx is equal to 4 sigma divided by E dash into root of a square minus x square. Okay, so investigating the strain energy released as the crack forms, we can find this by estimating the crack needed to bring the crack surface together again. The crack surface are brought together when applied stress is equal to sigma. So the energy required to close the crack of length c is the manner is therefore given by Wa is equal to integration of x is equal to minus c to plus c sigma d of x into d of, by 2 into d of x, that's equal to 2 sigma square divided by E dash. Okay, integration of x is equal to minus c to plus c root of a square minus x square into dx. If we reduce this equation, we will get the equation pi sigma square c square divided by E dash. This is the Griffith equation. Okay, so when crack growth, so in simply Griffith theory can be explained like this one. When crack growth, okay, when crack starts to growth, the material starts to release its elastic energy. Okay, release its elastic energy in order to oppose the growth of the crack. Okay, so the reduction in elastic energy is given as pi c square sigma square divided by E dash. So because of this release in the elastic energy, there will be increase in the surface energy, which is given by 4 gamma c. Okay, so the change in energy is given by del u is equal to 4 gamma c minus pi c square into sigma square divided by E dash. Okay, right. So when we reduce this equation, then we will get the Griffith equation as sigma f is equal to root of 2 gamma E dash divided by pi c. So at constant c is equal to c star, when sigma exits sigma f, the specimen fails. This is the Griffith equation. Okay, right. So stress criterion for a crack propagation. So cracks have a sharp tip and load to stress concentration. So if if you can see there's two diagrams, okay, one is having a sharp corner, another one is having a circular hole, okay. So the sigma maximum for both cases can be calculated by this formula, 2 sigma naught root of c by rho, whereas in this case for circular hole sigma max equal to 3 sigma naught, okay. So work done by crack tip stresses to create a crack is equal to energy of the surface faces. So sigma f is equal to root of E nu p divided by 4 a naught into c. So what is the protection against brittle fracture? So this equation is a Griffith equation, sigma f is equal to 2 gamma E divided by pi c, okay. So the removal of surface cracks is nothing but etching of a glass followed by resin cover is the one way of protecting the against brittle fracture when reducing the nu, that is nu is the surface energy, okay, that is equal to sigma f can be reduced, done by chemical absorption of molecule on the crack surface, introducing compressive stress on the surface of the molten glass solidified by cold air followed by solidification of the bulk, okay. So another methods to reduce this brittle fracture is short peening, carburizing and nitriding. So with this we can conclude this session. So thank you for your patience listening. Thank you.